What if the ultimate speed limit of the universe, the speed of light, suddenly changed? Would time, space, and life itself still exist as we know it? Let's find out. It's a simple change on paper, but the consequences are anything but. The speed of light, c, is more than how fast light travels. It links mass and energy in Einstein's famous equation, E equals mc squared. That tiny letter sets scale. Change it, and energy, mass, and how objects move are recalibrated. Relativity uses c as the backbone. It defines how space and time are stitched together. Space and time are not separate when c is involved. They're two sides of the same fabric. Change the speed limit and the rules that let GPS work, chemistry proceed and stars burn all change too. So even though c looks like a number, it is the scaffolding for everything physical. Let's imagine two extremes. First, what if light were slower? Imagine a beam that crawls. In a slow universe, light moves sluggishly even across a room. Time feels different. Causality stretches. Everyday reactions take longer. Video calls across continents could take minutes or hours. Real-time collaboration becomes impossible. Networks built on near-instant signaling would stutter. Latency would dominate economics, defense, and science. The starlight we see could be millions of years out of date. Many stars might have died long before their light reaches us. Our snapshot of the cosmos would be a far older photo. Cosmology becomes a lagged history. At atomic scales, electromagnetic interactions depend on c. If c is small, chemical reaction rates drop. Biology relies on those rates. Photosynthesis and nerve signaling could crawl. Life, if it exists at all, would operate on much longer timescales. Gravity and electromagnetic processes interact through c. Structure formation, stars, galaxies, planets could change or not happen the same way. Society built on real-time signals, markets, medicine, defense, faces new vulnerabilities. In a slow light universe, everything is stretched. Time, reactions, information. It's a quieter, older universe. Now let's flip the coin. What if light were faster? If light sped up dramatically, information would race across space almost instantly. Distances would feel smaller. Real-time global coordination becomes trivial. Latency vanishes, markets and systems operate at unheard-of speeds, but the same constant keeps relativity intact. If c is extremely large, time dilation effects that underpin special relativity weaken or collapse. Systems like GPS that rely on relativistic corrections would break. Navigation and timing infrastructure would need radical redesign. At extreme changes, electromagnetic forces change in balance. Atoms might not bind the same way. Chemistry could be profoundly altered. Material stability is at stake. Everyday matter might behave unpredictably. Faster c alters causality diagrams. Events that were causally separated could change their relationships, potentially breaking cause and effect in unexpected ways. Every instrument tuned to today's c would require recalibration. Experiments and engineering assumptions would be invalid. There are enticing possibilities: near-instant exploration, faster computation across distributed systems, and collapsed communication delays. But the paradoxes could be severe. Time-based laws we take for granted would need redefinition. Faster light makes the universe more connected, but less familiar. The price could be the collapse of the very laws that let atoms and life exist. Next, the deeper physics implications. Physics rests on constants. These numbers, including c, form the foundation of many equations and models. Change c and Maxwell's electromagnetism, general relativity, quantum electrodynamics, they all respond. Researchers would race to update theories. The public would see the consequences in technologies that fail or behave oddly. Small changes in constants can lead to wildly different universes, a central idea in anthropic reasoning. Gravity equations depend on how c relates to spacetime. Cosmological expansion and structure formation would be rewritten. Some universes might never form stars, others become hostile to chemistry. Our universe's habitability depends on a delicate balance. Beyond theory, infrastructure would need wholesale redesign. Communications, navigation, energy systems, all tied to electromagnetic behavior. But science adapts. New theories could emerge to describe a different c, though life as we know it might not survive the transition. Constants are the grammar of nature. Alter the grammar and the stories that can be told. and lived change. But could C ever have been different? Let's check the earliest moments of the cosmos. Some cosmologists have proposed that fundamental constants might have varied during the earliest epochs, including during inflation. If C were different in the very early universe, it could help explain puzzles like horizon problems and inflation. A temporarily higher C could allow distant regions to thermalize, offering alternate solutions to standard inflationary models. But evidence is subtle. Observations like the cosmic microwave background constrain how much C could have changed. In today's universe, measurements across decades show remarkable stability. Atomic clocks and spectral lines don't indicate large drift, so while it's a theoretical possibility in early epochs, current evidence points to a fixed C now, and that stability is crucial for life. Whether variable early on or constant from the start, the values we observe enabled complexity and life to emerge. Either way, C is central to our cosmic story. The speed of light isn't just a number, it's the foundation of reality. Change it, and the universe changes with it. From atoms to galaxies, from clocks to conversations, C underpins the rules that let us exist and communicate. Would you survive in such a world? Tell us in the comments below. If you enjoyed this deep dive, like, share, and subscribe for more mind-bending science from Physics Unboxed.